Hello students, this is Mr. Bornheimer, and today we're going to be talking about a few things in chemistry, but we're going to start with the ideal gas law. Now, as you can see on the screen, this is what we're working with, and if you recall from yesterday's class, we introduced the equation. We didn't necessarily go through one example problem, but you had for homework, you had to find the moles of gas in my classroom. Okay, so let's just recap. First of all, an ideal gas. Ideal means that it's a gas that's relatively small. There are gas particles that are huge. Some, like we talked about, I told you about one example, sulfur hexafluoride. It's a heavy gas. Wouldn't necessarily fall into the ideal gas category because it is a very dense, heavy gas. But like water vapor, oxygen, nitrogen, helium, these gases, bromine gas, it's actually kind of a little bit heavier, but some of the gases that are in the top part of the periodic table, they're small and they don't necessarily, they fall into the ideal gas category. Okay, so the ideal gas law is this law, PV equals nRT, and we addressed what each of these things mean. First of all, pressure, P, okay, and V was volume, N moles, R is our constant, and I'm going to kind of talk about that next, and T would be temperature. Okay, so really this law is useful for a number of reasons. You could be working with one gas and knowing the pressure, volume, temperature, you can find the moles of gas. Okay, if you know you have a gas, a particular moles or quantity of gas, and you know what container you're going to put it in, what temperature, you could predict the pressure. This is very useful because oftentimes when we pressurize gases, there's a certain extent, their containers have limits on how much pressure you can put in them. Like an air compressor has a limit on how much pressure can be in that container. So we know the volume of an air compressor, we know the temperature, usually room temperature, or the maxes and mins. Okay, and so we know what kind of compressor or the pump can put a certain amount of air in that tank, so we can kind of figure out how much pressure it can hold and build a container that is safe to do so. So these kinds of things are very important to us. Another really key distinction with the ideal gas law is that the ideal gas law, well, that's an example problem. Let's skip ahead a few here. The ideal gas law deals with things how they are currently. Okay, so to give you kind of a recap, P1 V1 over T1 equals P2 V2 over T2. Now, this is the combined gas law, and it includes my boy Charles, Boyle, and Gay-Lussac. Okay? All three of their laws are tied up in this. However, this deals with before and after. Okay, so how did something change? How was the gas before? And it changed into something after. Now, it's still a gas, but the conditions of the gas, either the pressure, the volume, the temperature, or all three, changed. So this is really something that happens over, and this is the key idea, time. Okay? Whereas the ideal gas law, this is here and now. There is no before and after. What is the current pressure? What is the current volume? What is the current temperature? And I can calculate exactly in this moment how many moles there are. So I had you do this, and we did it for the classroom. Okay, so we started with a pressure of 101.3 kilopascals. Okay, we said that the volume of my classroom was right around 140,600 liters. We said that the temperature in my classroom was right around 21 degrees Celsius, and important, you always need to convert to Kelvin. So we're going to add 273, and that becomes 294 Kelvin. Okay, 294 Kelvin. 273 plus 21 is 294 Kelvin. Okay, So, and now that I recall it, we might have messed up on the temperature yesterday in our haste. So if that is the case, please correct that at this time. Okay, and what we were trying to find is how many moles of gas are in the classroom. And we need one more piece of information. We need R. Okay, R, and if you recall from your I told you the page in your textbook, R is a value that was calculated basically by a lot of experimentation, and it's a constant that allows this equation to work. Okay, it's kind of like the key. Without it, the equation won't work for us, won't open for us. So what we need is this constant. And for our purposes, if we're dealing with kilopascals, liters, and Kelvin, the constant is 8.31. Okay, 8.31. The units of which are liters, kilopascals, over Kelvin, and moles. Okay, it's a constant. It kind of adjusts the equation to work. And there are actually different constants based on what pressure you're using. Okay, so if we were using atmospheres, this number would be different. But atmospheres is kind of an older unit. The current SI unit for pressure is kilopascals. Okay, so go ahead and click here. So anyway, there we go. Now, what we're going to do here is we're going to go ahead and figure out what is the number of moles, what is the quantity of moles in our container, or in our classroom, using all of this information. So we're going to go ahead and add this. So we always should start by writing our original equation, PV equals nRT. Okay, and we're going to put in our pressure, so 101.3 kilopascals. We're going to put in our volume, okay, which is 140,600 liters. And we're going to set that equal to N. And then we have R and T over here. Now, I'm not going to put R and T in yet. Anytime you're trying to find something in the ideal gas law, it is better to rearrange the equation for that variable. Some of you will put numbers in like this first. And though that is an okay way to do it, it is not ideal because the more you have to write, the more the chances are that you're going to make a greater mistake. So what I would highly recommend is that you actually rearrange the equation first. So instead of doing this, I would prefer if you did this with the R and the T, where you go ahead and rearrange and solve for N first. So I wanted to show you kind of how a lot of people approach this. The way that I recommend is rearranging the equation first. So we want to solve for N, so we're going to rearrange it for N. We'll divide both sides by RT, and the R and the T will cancel out on the right hand side, and you're going to be left with N equals PV over RT. Okay, so we can use this, plug in our information, and solve for the number of moles of particles of gas in our room, or so the moles of gas in the classroom. So let's go ahead and plug in our information. N equals PV over RT. The pressure is 101.3 kilopascals. The volume, 140,600 liters. R is that given value I was talking about, 8.31. And that will be given to you, okay? 8.31. I'm going to leave the units off for now. However, the units are incredibly important. And the temperature in Kelvin, let's kind of shoot back, take a look, is 294. okay, 294 Kelvin. Okay, at this time, you should pull out your handy-dandy calculating device. So, here's mine. And I have 101.3 times 140,600. Okay, it's going to be a rather large number. I'm going to divide that by 8.31 and then divide again by 294. And I get a rather large number of moles. Okay, N equals 5,800 and roughly 30. Okay, that is a lot of gas. Okay, that is a lot of particles. Now, interestingly enough, your book has a problem where it's dealing with gases, okay, especially air. And one of the things that it gives you, and let me see if I can find it here real quick. It is on page, let's take a look here. It is in the 300s here. One of the cool things about this problem is that it gives you the molar mass, or the approximate molar mass, of air. Now, you've got to remember, air is comprised of a number of different things: nitrogen, oxygen, argon, CO2, H2O, okay? But the approximate molar mass for air is 29 grams per mole. So, if we wanted to find the actual mass of the air in the room, we could do that by multiplying by the molar mass. So 5,830 moles times 29 grams per 1 mole. Okay, and if we set this up, our moles will cancel, and we'll be left with grams. Gives us almost 170,000 grams, or 169 kilograms. Okay, now that might not seem like a whole lot to you, but 169 kilograms, okay, is roughly or approximately the size of 3 adult human beings. So if you were to take all the air in the classroom and weigh it, it'd be equivalent of about 3 human beings. Okay, so that is pretty significant amount of mass. Okay, that is huge. It's a little less than 3 humans, about 2.5. But since you can't have half a human, I guess you could get a small human. Then it's really quite a lot of mass. We don't think about the air in the room as having mass, but it does. Now, this is, of course, assuming that there's no desks or people or anything else in the room. But there is a considerable amount of mass of air in the room. Okay, so this is the ideal gas law. And I think that for the most part, you're getting the hang of plugging numbers in and working through numbers. Okay, so we're going to kind of move on to another idea today. And this idea is a little bit less like the other laws, Charles, Boyle's, Gay-Lussac's ideal gas law, combined gas law. This is this idea that Avogadro came up with, my man Avogadro. So Avogadro had this hypothesis, okay? Like all good scientists, he asked questions, he made predictions, and he said, what if we were to look at the gas up close? Okay, if we were to look at this gas up close, okay? So if we were to look at it up close, it would look something like this. And Avogadro said, you know, we here at our level, we think of big things and little things as being significantly different. But at the gas level, okay, the size of these particles doesn't really make that big of a difference. Notice these particles are larger than these particles here, and the ones on the left are larger than the ones on the right. However, okay, when it comes to filling up a container, there is so much free space. Okay, all this free space in here that the particles don't really take up that much more space, even though they're larger. And this doesn't seem like that big of an idea. Okay, so what? But what it meant for Avogadro, what it means for us, is that really, we can measure a space, a volume, and the gas in it, and it doesn't matter how big the gas is, these laws work for us. This is Avogadro's hypothesis. So you know that whole idea of STP and 22.4 liters per mole? That's where this comes from. So part of this unit is kind of revisiting the 22.4 liters per 1 mole of gas at STP. Okay, and if you recall, this is actually from your mole roadmap. And if you have your mole roadmap, it might be very useful for you today to kind of look at this and just maybe pull it out, okay? So what we're going to be doing is we're going to just work with this a little bit. We're going to say no matter what size gas you have, if the gas is at STP, there will be 1 mole of gas in 22.4 liters or in a 22.4 liter container. Now, when we first looked at this, STP was just something we had to know. But now, it's a temperature, it's a pressure, it's a volume, and it's moles. It kind of all comes back to what we've been talking about, PV equals nRT. So that's kind of how it all fits in. Just so you all know, this diagram here that I was looking at was on page 347 in your text. And it's worth reading it, okay? The caption on the thing says, the volume of a container easily accommodates the same number of relatively large or small particles as long as the particles are not tightly packed. And in a gas, they won't be. If you recall from me throwing ping pong balls around, the particles are not tightly packed. As a matter of fact, if I was in an atom, okay, and I wanted to see the next closest atom in a gas, I would have to go a mile away just to see that atom. They are incredibly spread out. All right, so there is a great deal of space compared with the volume occupied by the particles. When the particles are tightly packed, large particles take up more space than small particles. But when they're in the gaseous state, they take up the equal amount of space. Okay, so large particles, small particles, doesn't really matter so much. And because it doesn't matter which gases take up which space, they're all going to have the same kind of pressure, they're all going to have the same number of collisions. Okay, and so this led to a guy by the name of Dalton to come up with this, what we call partial pressure law. Okay, this will be the last kind of tidbit of information we're going to be talking about today. It's called the partial pressure law, or Dalton's law of partial pressures. Okay, and information about the partial pressures can be found on page 350. Okay, so if you're curious in your text, you're looking at it and you want to kind of draw attention to it. If you're watching this video and you don't have a textbook, that's fine. I'm going to go ahead and explain it. Okay, the example they use is a great one. When gases are mixed, all right, so first of all, we're dealing with mixed gas, meaning that there are different ones, different types of gases involved. The best example is air. Okay, when you have mixed gases like air, the pressure of each component makes up the total pressure. Okay, so for instance, air is composed of about 78% nitrogen, okay, or N2 gas. It is composed of about 21% oxygen. Okay, it's composed of about 0.04% CO2. And there's actually about 0.93 or, yeah, I mean, it's a pretty small amount. So if we see this is 99%, so let's just say 0.96% argon and other small gases. Okay, so this is air. And if we were to measure just the pressure of the nitrogen, the oxygen, the CO2, and the argon, we would see that they each contribute to the pressure of air, but they're not all at the air pressure. Okay, for instance, air pressure at our level, at sea level, is 101.3 kilopascals. okay? You should star this. Know this value. Air pressure at sea level is 101.3 kPa, or kPa, kilopascals. So, it's not actually called kPa, by the way. Just throwing that out there. But it's kind of fun to say. So if you want to say it, kPa, okay, it's kind of fun. But nonetheless, I digress. What we're focused in on here is that this is the total pressure. So nitrogen contributes to that pressure, oxygen contributes to that pressure, CO2 contributes to that pressure, and argon and a little bit of the others contribute to that pressure. Okay, so there's this table in your book. It's a great table, and it shows that nitrogen, N2 gas, contributes about 79.11 kPa. Okay, that's what nitrogen's pressure would be. And oxygen's pressure, okay, is 21.22 kPa. Notice that their pressures are very similar to their percent of the total. Okay, so 78% of air is nitrogen, almost 78 kilopascals is its contributed pressure. Okay, they're very similar. Carbon dioxide, so CO2, contributes 0.04 kPa, and argon and others, contributes 0.93 kPa. Okay, and if you add all those up, so take out right now your handy dandy calculating device. Okay, you should be taking it out, so I'll wait. Okay, some of you had to rummage through those serious backpacks. You never know what you'll find in there. So now let's plug it all in. 79.11 plus 21.22 plus 0.04 plus 0.93 equals 101.3. Whoa! No way. Yes way. It is. Okay? So if you add all of these up, shabam, it is 101.3 kPa, shabam. There it is. So if you add up, if you have a bunch of gas in a container, and you know what percent gas is what, you can actually find what that individual percent of that or what the individual pressure of that gas is. Okay, so that's kind of cool. We can break it down. We can look at it. So there is an example of this. It's some example problems in your book. So let's go ahead and do one of these. Okay, and here's how it goes. Okay, it's number 38. So if you're curious which number I'm actually working with, and it says a gas. I would like it if you all wrote this down as well. Okay, a gas mixture containing oxygen, nitrogen, and CO2, so carbon dioxide, has a total pressure of 32.9 kPa. Okay, that's the total pressure. Now, it says if the pressure of the O2 is 6.6 kPa and the pressure of the N2 is 23 kPa, kilopascals, what is the pressure of the CO2? Okay, that's the question. So you might be trying to figure out how to approach this, and that's fine. Why don't you go ahead and take a moment, okay, right now, pause the video and figure this out. Okay, go ahead and pause it right now. Okay, the video should have been paused, and so hopefully it was. If not, then you should be working through this problem right now. I'm going to kind of sum up some of the other things here, and I will come back to this in just a moment, okay? So give you a chance to work through it, okay? So while you're working through it, I'm going to go ahead and write down your homework on the next slide. And if you did pause the video and you are watching this right now, you can just go ahead and you can write down this. The homework for tonight is going to be focused mainly on PV equals nRT. Okay, so really practicing this equation. And there's going to be a little bit on Dalton's partial pressures. Okay, so Dalton's Law. And then also I want you to kind of recap the 22.4 liters per 1 mole, okay? So this is going to be a little bit more homework than you're used to. There's probably going to be just a couple more equations than you're used to, but not many more, okay? So what I want you to do is on page 343, I want you to try problems number 24 and 25, okay? There's some great example problems in the book right next to those that you can use to kind of help guide you. And we're going to go over these tomorrow when I come back. If you have any questions, please send them to me ahead of time so that I know kind of what maybe you struggled with or whatnot when we come into class tomorrow. Okay? Next, I want you to go ahead and this is more mole roadmap. So these next couple shouldn't take you very long at all. I want you to do on page 348, I want you to go ahead and try numbers 31 through 34. Okay, so go ahead and do those. And then lastly, on page 351, I want you to do problem number 37. Okay? So 24 and 25, 31, 32, 33, and 34, and 37. It's a grand total of 7 problems. Okay? Have them done for tomorrow. I will collect them. Okay? I will collect them. So make sure that you're turning them in, that you get a chance to turn them in. Please do not turn them in late. Okay? It'll be one of the larger assignments for this unit, and it'll be worth more points. It could be a really great boost for some of you, and it could hurt some of you if you don't get it done. Okay. All right. Let's get back to this problem. If you've worked it through, basically what you should have done is you should have taken your total, okay, 32.9 kilopascals, and said, hey, that's equal to the other ones plus what I don't know. So it's equal to the pressure of O2 plus the pressure of N2 plus the pressure of CO2. Okay. And I know these other ones. Okay, I know that the pressure of O2 is 6.6 kPa, and I know that the pressure of the N2 was 23 kPa. So what I have so far is 32.9 kilopascals equal to 29.6 kilopascals plus the pressure of CO2. And what I can do is I can subtract 29.6 from both sides. That's it. So 32.9 minus 29.6 is 3.3 kilopascals. And that's what you should have gotten for your answer. Okay. All right, we're about a half hour into this video. We've gone through quite a number of different things. Okay, we started with this ideal gas law, and we kind of recapped that. We answered yesterday's question, okay, and we found that You have about 5,830 moles in the classroom, and we can even use grams to find that. And there's a great problem in your book that also deals with that. Okay, and then we talked about Avogadro's hypothesis, and he said that, hey, big particles, little particles, it doesn't matter. And that's kind of where this idea of 22.4 liters per 1 mole came from. Okay, at STP. It's very important. And this ties in nicely with the ideal gas law because of the volume, the temperature, the pressure, and the moles. Okay, so all of those components there. Which led us into Dalton's law, looking at specifically pressures. It's a very simple law. You have it on your flashcards. You can go ahead and visit it there as well. And that leads to your ability to kind of go ahead and try these problems tonight. Okay, and we can review any questions you have in class tomorrow. I'll give you 5 minutes, so make sure you come with your questions ready. Okay, but I will come around and check that the homework was done ahead of time, and I will be marking your papers to see that it was done so you can't complete it while we're working through some of the problems. Okay, so make sure it's done before you enter my classroom. Okay, any questions, email me. Otherwise, I hope you folks have a wonderful day, and I will see you tomorrow in class. Thanks for watching.